Welcome to the Chapter 9, Part 3 and 4 video on sequences in series. We're going to be looking at infinite sequences, specifically at the types of sequences that are called arithmetic and geometric. We're going to be looking at summation notation and then finding the sum or series of those sequences. Why is this important? Well, infinite sequences, especially those with finite limits, so the ones that we'll say converge at a limit, are involved in many key concepts of calculus. And then summation, so adding those together, is really important for statistics as well as calculus. And you'll see as well as things like construction and making sure that there are enough seats in a baseball stadium or things like that. So we're going to start out with defining sequence. We already kind of defined it as a pattern, but specifically, this is a way of studying patterns, looking at the progression of numbers. So we have a finite sequence. That means it ends. There's some ending point. If I'm looking at the number of seats in a baseball stadium, for example, there is a final row. So that means that would be a finite sequence, or there could be an infinite sequence. And that could be something like theoretically that we're thinking about. It could be something like I have a loaf of bread that I cut in half every time I make a meal. That would be technically an infinite sequence because I can always take half of something. Okay, so sequences have a rule. We saw last time an explicit form that gives you the nth or kth number in the sequence, but not all of them do. Sometimes there's not a way to write that pattern in an explicit form. So let's start out with an arithmetic sequence. We're going to be focusing mainly on two types. Arithmetic is our first type. And in an arithmetic sequence, we have a sum number that's added over and over and over again. And that number is called the common difference, and we denote it with a D, D for difference. Okay, so essentially, if I have a pattern, let's say 1, 5, 9, 13, and so on. So this is infinite because it doesn't end. I can look at this pattern and I can say, okay, what is the pattern? Here I added 4, here I added 4. I can never just take my first stab at a pattern to be the one that will work. In this case, I knew it was an arithmetic sequence, so I knew I was adding something over and over again. But I should always check 2 or 3 times to make sure that that is truly the pattern. So in this case, because I'm adding 4 every time, the distance between my numbers is 4 units. So our common difference is 4. Okay, I'm adding 4 each time. So D equals 4. Okay, notice if I call this first number A or A1, sometimes we'll denote it as the first A, then this would be A2, A3, A4. Those subscripts are just saying which term is it? Is it the first term, the second term, the third term, and so on? And if I wanted to find something like the 10th term, I would be adding 4 over and over and over again, but I did not have to add 4 to the first term. So I'm actually adding it n minus 1 times. Okay, that's where this formula here comes from. I start out with my first term, in our case 1, plus, and I like to write the D in front, times n minus 1, because that shows me I'm multiplying my common difference, which is 4, times n minus 1 times. Okay, so what does that mean? Well, I had to add 4 to get the second term. I added it twice to get the third term. I added it 3 times to get the fourth term. So to get the 10th term, I will have added it 9 times. So in this case, to find a 10, I would say I started at 1, I added 4, but I added it 9 times. So 9 times 4 is 36. So my answer here is 37. Okay, that is called the explicit form. The other way that we can write this is by finding what's called its recursive form. Recursive means just based on the last number. So if I'm looking for a sub 10, I can look at my previous number. So if I'm looking for a 10, that would be a 9, and then adding my difference plus 4. So in order to calculate recursively, I need to find all of the ones before it, because then a 9 will rely on a 8, and A8 will depend on A7, and so on and so forth. So recursively, if I have the previous terms, recursively is usually easier. If I don't have the previous terms, then explicit will be easier. So this was explicit, and this one is recursive. Okay, so let's go ahead and take a look at an example. Arithmetic sequence, we have -2, 1, 4, 7. What is the pattern? Well, -2 plus 3 gives me 1. 1 plus 3 gives me 4. 4 plus 3 gives me 7. So my common difference here is 3. My common difference is 3. How do I find the 10th term? Well, I can say A1 was -2. Then the second one is 1. The third one is 4. The fourth one is 7. I need to find 6 more terms. The fifth one will be 10. The sixth one will be 13. Seventh will be 16. Eighth will be 19. Ninth will be 21. 10th will be 24. Hopefully I didn't make any mistakes there, right? So I think I did. 10, 13, 16, 19, nope. I look okay. Something didn't look right. It's actually 22, not 21, right? 19 plus 3 is 22, and then plus 3 is 25. Okay, so A sub 10 is the 10th term, which is 25. If I was finding the 17th term, the 20th term, the 100th term, I don't want to have to make that whole list. So the other way we can find that is by saying to find a 10, I started at -2, and I'm adding my common difference, which is 3, but I'm going to add it, to find the 10th term, I add it 9 times. -2 plus 3 times 9 is 27, is 25. Much easier to do that if you know the explicit rule. So let's actually find the explicit rule next. Our explicit rule, A sub n equals, A1 plus D times n minus 1. So our first number is -2 plus 3 times n minus 1. Notice this is very, very similar to how we found A10 because we're using the same formula. So this will be -2 plus 3n minus 3, which is 3n minus 5. So here, A sub n is 3n minus 5. I'm going to go ahead and box these so we can see those are my answers. And then the recursive rule, always an equals an minus 1 plus the difference, in this case is 3. So recursive A sub n equals A sub n minus 1 plus the difference. Now my difference can be negative. If I'm subtracting every time, then my difference would be negative. Okay. So that is our arithmetic sequence. Next, we're going to look at geometric sequences. For our geometric sequences, instead of adding every time, we are multiplying every time. So again, I'm going to call this A1, A2, A3, all the way up to A sub n. And those subscripts, the little numbers, are just telling us what order we're going in. It tells me A sub 10 is my 10th term. This time, since we're multiplying every time, we have what's called a common ratio. Common ratio is the number that's being multiplied every time, just like our common difference was the number that's being added every time. Okay, so in this case, we again have our explicit form and our recursive form. Recursively, I'm multiplying every time. That's how we can say this. In order to find our next term, we take our last term times r. In the explicit form, since we're multiplying by r every time, we did not have to multiply by r to the first term. That's where this n minus 1 comes from. So we saw the explicit form for an arithmetic sequence used multiplication because multiplication is repeated addition. For the geometric sequence, we see that it's using an exponent because an exponent is repeated multiplication. Okay, let's look at an example. In this example, we have a geometric sequence. We're told that it's geometric. If I didn't know, I might start out by saying 2 plus 4 is 6, but then it would be 6 plus 12. Those don't match, so I know it's not an arithmetic sequence. So if I'm multiplying, that would be a times 3. 6 times 3 is also 18, so I know this is geometric, and my common ratio is 3. To find the 10th term, I can keep going with this pattern, times 3 times 3 times 3 times 3, but just like we saw in example 2, actually, I think I removed example 1 from the notes packet. So if you were looking back for that, I removed it from the notes packet. But in our last example, when we were finding the 10th term, we can build up from the first term and find all 10 of them, or we can use the explicit form. So I start with a sub n equals my starting value times my common ratio n minus 1 times. Because I'm multiplying, I get an exponent. So my starting term was 2, my starting value is 2. My common ratio is 3 raised to the n minus 1. If I'm looking for the 10th term, that's going to be 2 times 3 to the 9th. Okay, I'm going to go ahead and use my calculator for this. 2 times 3 to the 9th is 39366. A10 equals 39366, 39,366. Okay, what is the recursive rule? Well, the recursive rule says a sub n takes the last number, which was a sub n minus 1, times my ratio, which is 3, or I can write it as 3 times a sub n minus 1. I'm going to put parentheses so that we can see that that's not a sub n minus 1. It's not just 1 less than the previous term. It's a sub n minus 1. I'm looking at the previous term. Okay, these are not the same. Am I subtracting 1 from my term, or am I going 1 place back in line? Okay, part D, the explicit rule, we already used this when we found part B. That is 2 times 3 to the n minus 1. Okay, so that's arithmetic and geometric sequences. Next, we're going to look at what happens when I add those together. So if I wanted to add, like we saw in class, the numbers 1 through 100, I can write that as the sum. And we use, again, this is a Greek letter sigma. We can say the sum from 1 to n. So if I wanted to write the sum from 1 to 100 of just the numbers, I can write it as 1 through 100. Now k will substitute with starting with 1 all the way up to 100. So I say my first k is 1, then my next k is 2, and my next k is 3, and we would keep going, and then the sigma means I'm adding these. So I'm going to add all the way up until my last number, which is 100. So this is like where I start and where I stop. So I'm adding up from 1 to 100 of just the number. Now, when we say a sub k, that means we're going to add up the terms of a sequence. So now we're using summation notation to find the sum of a sequence, and that is called a series. Okay, now notice this has an n and also a k. So what are the difference between the n and the k? The n tells us where to stop. N is our last number to substitute. K is the variable that we're substituting into. Okay, so we will see the role of n and k change sometimes. So we can have a sub n as the argument of the sum, but really what we're looking at is k is being substituted because it's in our expression. So we're substituting starting with 1 and going up to n. We don't always have to start with 1. We could start with 5. We could start with 7. Okay, so it's just starting and stopping points. So let's take a look here. Whoop, here we go. At the sum of a finite arithmetic sequence. So finite means it ends. So I'm going to have a number that it stops at. Arithmetic, meaning I'm adding between each term. Okay. And then we're finding the sum of the sequence. So if I'm finding the sum of the sequence that ends, right, this doesn't have a dot, dot, dot at the end. If I had a plus dot, 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 that would be infinite. But I have a last term, so that makes it finite. If I want to find the sum of that, what I can do is I can take the first one and the last one, add those up, a1 plus an, and then you can think of it as dividing that by 2 or dividing n by 2. Okay, so how many terms were there? Divided by 2, multiply those together. Depending on which one is even, or if neither of them is even, it might be easier to do a different order of operations, right? So following order of operations, I can multiply these in whatever order I want. I can do the sum divided by 2, I can do the n divided by 2, or I can multiply the sum times n and then divide that by 2. This is one way of looking at the sum of a finite arithmetic sequence. That's a formula, okay? The other way is to look at that a sub n, that's our nth term, is going to be a, our initial term, a1, plus our common difference times n minus 1, right? So if I substitute that in for my a sub n, I come up with this second formula. So we have two different formulas that we can use to find the sum of a finite arithmetic sequence. I think the first formula tends to be easier. Find a sub n and then calculate it that way, but it's up to you which one makes more sense. Okay, so that is finding the sum of a finite arithmetic sequence. Let's do an example. In this example, we want to find the sum of the terms. A corner section of the stadium has 6 seats along the front row. Each successive row has 3 more seats than the row preceding it. If the top row has 24 seats, how many in the entire section? So this is a section of a stadium. I'll just draw it like this. Our first row has 6 seats. Our last one has 24 seats. So this was 6 seats, and every next row has 3 more. So my next row will have 9, and the next one will have 12, and so on, okay? So I wanna know how many seats there are. So this is going to be the sum from our first row to our, I don't know which row that is, right, of our sequence. So the first step here, we can find which row we're going to, okay? 24 equals which row? So I started with 6, I added 3, n minus 1 times. If I solve this, it will tell me which row that is. That's the nth row, okay? So I'm gonna say 6 plus 3n minus 3, 3 plus 3n minus 3, 21 is 3n, so n is 7. So that tells me this is the 7th row. This was my first row, that's my 7th row, okay? And then we want to say, what are we adding up? So I'm adding up my sequence here. 7th is my stopping point from 1 to 7 of, well, this is 3, or, well, yep, okay. Try that again. I found my explicit form here, right? Or here. 3 plus 3n. Okay, but really, that's not super important. What I need to know is my formula, n over 2 times a1 plus an. Okay, so that's 7 over 2 times, I started with 6, ended at 24. So this is 7 times 30 over 2. I'm going to divide the 30. 7 times 15, which is 105 seats. Okay, so we did need to find which row is my top row. It's the 7th row. And we did that by substituting into the explicit form. Okay, I wrote it in summation notation. but really we just need the parts of the summation notation. We need to know where it ends. We need to know the value that it starts and ends at, and then we can put it into the formula. Okay, so there are 105 seats in this section of the stadium. If this was, it's only 7 rows, so really we could have just found each row number and added them. Absolutely, you can do it that way. If this was 30 rows, that's going to be much more time consuming and tedious to work on. So the formula will be much more helpful the larger the section is. Okay, our last topic is geometric sequences. So our geometric sequences are the ones that multiply. So we have a different formula here. And this formula is when I add up a sequence where to find the next term, I multiply each time, right? That was what a geometric sequence is. So that's a formula you want to copy down. And for geometric sequences, we actually can look at both the finite and infinite case. So let's talk about infinite series. Remember, when we were looking at algebra or arithmetic sequences, we said they can end or they cannot end. And when we looked at series, we looked at the case where it ends. What if it doesn't end? Okay, for an arithmetic series, meaning I'm adding them up, if it doesn't end, then it diverges. It's just going to keep getting bigger and bigger and bigger. Okay, for a geometric sequence that can end or not end, then we can find the series for that sequence depending on the common ratio. So if the ratio is less than 1, if it's a proper ratio, if it's a fraction, whether it's positive or negative, then that series, the series, the sum, will converge. If it does not end and the ratio is not a fraction, then it will diverge. If it ends, we can always find the sum. Okay, so here is another sum. This is another formula. This is for geometric, where my common ratio is a fraction. If my common ratio is not a fraction, then it diverges, meaning that it does not have a sum. It would just keep getting bigger and bigger and bigger. It would go to infinity. Okay, so let's look at our last example here. In this example, we want to find the sum of the infinite geometric series. So the first thing that we want to do is determine if it converges. Which part of this series is my common ratio? Well, if we think back for a geometric sequence, a sub n was my first a times r to the n minus 1. So r is the one that's the base. R is the base, meaning it was raised to a power. So that means this is my r. R equals 0.25, which is less than 1. So this converges. And then we need to use the formula. So the formula is a divided by 1 minus r. A is 2 divided by 1 minus 0.25. 2 divided by 0.75. If I simplify this fraction, and remember you can do that on your calculator, this is 8/3. Okay, so really this last section is mostly just using formulas, and I have those formulas here for you on a single slide, easy to access. I highly recommend you copying your own copy of this. Don't just print it out, because being able to reference it and understand the notation is just as important as being able to substitute into it. Okay. I know that this video was a little longer. I apologize for that. It's so that you don't have to study over break, but we will answer questions together in class.